Hello, good morning to everybody, and welcome to the 16th Uranus webinar, which is regarding this Intercomparison IC2021 area of passive area dosimeter systems, a review by organizer and participants. I am Arturo Vargas. I am the chair of the Working Group 3 regarding environmental dosimetry. I'm working at the Technical University of Catalonia in Barcelona. So let's go a little bit of an introduction of what is Uranus and where we do this kind of intercomparison, in which framework, and a little bit of the history of the different intercomparison and tasks we are doing in our working group. So in Uranus, we are more than 600 active scientists. And here you can see also a map in the right side of the different voting members distributed in all Europe. So these scientists are grouped in 8 different Uranus working groups, plus one pilot group. So you see here the different working groups, and the working group 3, as I said, is the environmental dosimetry group, where I am the chairperson. Which are the main activities of Uranus? So Uranus is the coordination of these working groups, and these working groups, they promote technical development and its implementation in routing work, also contribute to harmonization within Europe, and always perform scientific research. In these working groups, we also organize intercomparison and benchmark studies. We organize scientific meetings, conferences, training activities, winter schools, and these kind of webinars that you are right now. Also, it's important, our annual meeting, it's every year, and there are more than 300 participants in each one. So what about working group 3, the environmental dosimetry group? So this group is divided in 3 subgroups. One of these, the first one is the spectrometry system for environmental dosimetry. Is devoted more in early warning networks in emergency situation, yes. And we have different work package regarding calculation of HR10 with the spectrometry detect monitors, spectrum analysis systems, harmonized systems, and also these airborne spectrometry detectors. It was in fact a webinar in September 2021. Then there is the third group, the working group, the subgroup 3, which is regarding the radon, which the leader is Annette Rodberg from QTV. It was created recently because mainly this new regulation of rules, ICRP 137, yes. And we have this subgroup 2, which we are the webinar of today is in the framework of this subgroup 2, which is regarding this passive environmental dosimetry, and it's created in 2014, and we have a new responsible of this working group, subgroup 2, which is Christian Nava. I think it was at the beginning of this year, or just in summer. There are 2 main tasks here. The task 1 is the current status of passive dosimetry system used in Europe. There are questionnaires around all Europe in order to see the status. And the task 2 is the organization of comparison. And let's go a little bit more inside them. So this is the 2 questionnaires has been carried out. And okay, we have different questions there. They were answered by different labs, and we have analyzed, in fact, Maria Morduk led the analysis of these questionnaires. And if you like, you can go to the Uranus report of review of passive area dosimetry system using Europe to see the results of this questionnaire. And also it was the 5th Uranus webinar was regarding this questionnaire. Then let's go to the comparison history. Okay, it was the first in comparison. It took almost 2 years, and in 25 to 26, 7, it was organized by PTV in cooperation with the German Irradiation Association, 40 systems, 10 participants. Then after some years, started the second comparison, also organized by PTV, and it was a little bit more of system, 20 system and 12 participants. After that, it was what is called the first Uranus comparison. It was organized inside Uranus, and it was from May 2014 until October 2014. It was called IC Environmental 2014. And so the number of system increased, and also number of participants really in a big number right now. And it was more than 520 exposed dosimeters, and you can see here the publication of these results. Then we have an intercomparison was carried out together with a European project, which was the European project called Preparedness in the framework of Euramed. And in this intercomparison, the participant was 34 and 38 systems, and more than 700 dosimeters were exposed. So you can see here also in this slide the different PTV facilities that was used for the comparison, and we like to know, okay, influence of the cosmic radiation, of the terrestrial, of the inherent contribution, and also what about the irradiation facility. So we have this no underground lab where there's no radiation, the cosmic where you have a lake, and then we have the irradiation systems. Then we have another kind of comparison, which are we call it IC, the year of the comparison and count. This is the name that we put, and this is more regarding that one lab, in this case the KIT laboratory, they send to the different labs that irradiate the system that they have for irradiation. So this system, this detector, has been irradiated by the lab, and then they coming back to the kit in order to be read and to see what about the results of the irradiation process. And you can see here a slide of different of the deviation of the reference of the laboratory in percentage, which is pretty good results of the different labs. And then this is the last one. This is the IC2021 area, and this is the comparison that we are going to see today. What about this? The comparison, the number increased a lot, 66 participants, 47 different institutes, and also from other continents also. And in this case, okay, the challenge of this comparison was to measure additional small quantities of those that was irradiated additional to different detectors that was exposed during a period of time in environmental conditions. But you will see the different presentations of these people here. So you will see an introduction, an overview of the intercomparison by Julia Aslan from KIT. Then you will see the results of the specific from a team, from the CMAT team. This will be done by Rafael Rodriguez. And then you will see what about the feedback and the conclusion of this intercomparison, IC2021 area by Laninski. And also I would like to present or to show here which is going to be the moderator of the session, of the webinar, which is Nava, is the responsible of this subgroup 2. And so please, any question you like to do, put it in the question and answer in the chapter. So moderator Nava will manage these questions, and after the 3 presentation, they will be the answers and the comments of these questions. So just enjoy the meeting, and this is all from my side. So thank you very much.
Okay, so good morning also from my side. Thanks a lot, Arturo. As Arturo said, my name is Nava. I'm currently chairing this wonderful subgroup full of beautiful people, and I'm very happy to introduce 3 of them to you today. So the beginning is done by Julia Aslan. Julia is a colleague of mine, also working at KIT, as you saw on one of the last slides, and she will give you a general overview over this intercomparison and show some results of the intercomparison, as she was one of the persons being part of the organization group. Have fun.
So, hello everybody. So I'm going to present the Uranus intercomparison of the passive area dosimeter systems, which was carried out between May 2021 and April 2022. So first of all, I want to introduce the organization group, and mainly I would like to thank my colleagues for this great and successful cooperation. So thanks goes out to the coordinator Christian Laninski and the administrator Christian Gärtner from the Cyberstorf laboratories in Austria. My colleague Christian Nava, you already seen, from the KIT, and Maria Duch from UPC in Barcelona in Spain, Thomas Hanninger from the Mirion Technologies in Munich, Germany, and Jelka Knezovic from the Rudolf Bošković Institute in Zagreb, Croatia. So, Arturo already mentioned the challenge of this intercomparison. It was measuring additional really low irradiated doses under realistic measurement conditions. So we had 3 scenarios and which were provided, and the participant could choose between 3 months outdoor exposition and 3 months indoor exposition and 6 months outdoor exposition. So for each system, 12 dosimeters were sent to the KIT, 6 were needed or used for the background determination, and 6 dosimeters were used for the additional irradiation, with 2 different doses you can see here. It was 150 microsievert and 300 microsievert. So, as usually, we started the announcement with a newsletter and a questionnaire before the intercomparison, and all the interested person got a link to the online platform. You can see here this user interface for this online platform. Yes. So the participant had the opportunity to register their systems in this platform, and this was developed by the colleagues at Cyberstorf laboratories, and all the communication, the exchange of information, and the data, also the response of the values was carried out via this online platform. So we had 66 dosimeter systems which were registered for this intercomparison. These were 47 institutes from 20 countries, and you can see, as you expected, a lot of red marks in Europe countries, but also we had some participants from non-Europe countries like Canada and Argentina and Japan. And one interested participant from Morocco is missing here in this chart because the dosimeter didn't arrive in time at the KIT because we had problems with the customs, so they were stuck at the customs. And another problem with the customs we had with the dosimeters from Argentina, so the participant couldn't provide his dose values in time for the same reason, because the dosimeters were also stuck on the return shipment. But it's quite nice to have so many different participants. And in this intercomparison, 70% of the dosimeter systems are based on thermoluminescence detectors, 12% being RPL, followed by OSL systems, and film with 6%, and one system was based on a combination of TLD and RPL. So on this chart you can see here the numbers of detectors per dosimeter system, and the larger part uses 4 detectors per system, and followed by 2 detectors in 1 dosimeter, and the next larger bar is single detector systems. And as you can see, there's a great variety, up to 10 detectors. But 10 detectors in 1 dosimeter is the max. So for calibration, about 80% of the participants use cesium-137. Some participants did not specify their reference quality, but strontium, yttrium-90, X-ray, and cobalt-60 was also used. And this chart shows the lower measurement limit dependence, and all systems are stated to be capable of measuring dose values higher than 105 microsieverts. So we decided that the lowest extra irradiation dose should be 150 microsieverts. And here you can see the distribution of the measurement period and the conditions. And the green part is the majority, so they have chosen 6 months outdoor and 3 months indoor and 3 months outdoor are about the same. So here you can see the outdoor field, which was an area of 74 square meter at the KIT. This was an area that was not accessible to the public, and we hung 560 dosimeters at the same height. I will show you. In this picture, you can see it a little bit better. So we hung them with their reference point at 1 meter above the ground and with an equal distance from each other. And you can see all the different environmental dosimeters who took part in this intercomparison. Now to the indoor exposition. So the indoor measuring field was a normal office at a KIT. So we hung 276 dosimeters, something about 2 meters above the ground. And also you can see here a lot of different workspace dosimeters. And you can see some of them are symmetrical in their design, others were very flat, and a lot of personal dosimeters were used. So, and roughly in the middle of the exposition period, we irradiated the dosimeters with 2 different values I already mentioned, and also simultaneous irradiation were done of 3 dosimeters per dose. But I will give you here some more impression of the irradiation which were performed. So these irradiation were performed at a calibration laboratory at the KIT. So this laboratory is accredited to ISO 17025, and on the right side you can see some more impressions or pictures from the laboratory facility. So in the middle you can see the irradiation unit from the front view, and an animation from the irradiation unit from the side view the bottom, and in the middle, the big picture in the middle is the setup of the irradiation of the Uranus dosimeter. So all irradiation were performed according to the standards of ISO 4037. So we irradiated with cesium-137 free air, as you can see in this setup, and with a 0-degree angle to the reference point. And if the dosimeter size permitted, 3 dosimeters were irradiated simultaneous, of course. But you already saw a picture of the environmental dosimeters. There were some dosimeters which are a little bit bigger. So the simultaneous irradiation was not possible. We used an irradiation field diameter of 46 centimeters with an ISO dose of 98%. And finally, the KIT provided a calibration certificate for each dosimeter system. So now, here we go, you can see some results. So you can see the reported dose values at the date of the reporting. This is the reporting number, which was assigned at the day they were reported. And the reporting numbers from 1 to 51 are used for the 3-month systems, and the reporting numbers from 52 to 65 are used for the 6-month systems. And as you can see, most values are within an expected dose range, but there are also some significant higher values, and this is due to the transport dose contribution. So what we did as the next step was a calculated net dose. It's the value of the 6 irradiated dosimeters after subtracting an average background dose. And you can see also the black horizontal lines, which are equal to the reference doses 150 microsievert and equal to 300 microsievert. And I will do a real quick jump to the next chart because it's almost the same. It's the same chart, but for a better presentation, we sorted the values according to their deviation from the ideal response values equal to 1. So yeah, and you can see a lot of systems performed very well. And yes. So one important point was the assessment of conformity. So we decided to apply response limit to the certificates. And for this, the ISO 4047 provides an appropriate trumpet curve. You can see here the parameters we used and the lower and upper limits we calculated for both those values. And here you can see a graph with these trumpet curve. It's in red, and the reference values in orange for 150 microsievert and the reference values for 300 microsievert. And with these criteria, 93% of all results are within the limits. So in total, 53 dosimeter systems passed the criteria with all irradiated dosimeters with 0 fails. You can see it in the green area. So the orange area is with 7 dosimeter systems, which had 1 single fail, and the red area is with 5 dosimeter systems that had more than 1 fail. And yes, so more detailed information can be found in the Uranus report. You can download or even get this free available Uranus report on the website, and you can see the link here. So thank you for your attention.
Okay, thank you, Julia. For those of you who joined the webinar after Arturo's introduction, just again, the information, if you have any questions concerning one of the 3 presentations, just write them in the Q&A section of our chat, and we will try to answer them after the presentation. Okay, as you now have a general overview, you know what happened during this intercomparison. The next one in line is Rafael Rodriguez from CIEMAT in Madrid. He was one of the participants, or his institute was one of the participants of this intercomparison, and also of some of the intercomparisons before, which Arturo also mentioned. And he's now going to show us the results from CMAT compared also to the results of the intercomparisons in the past. Okay, here we go.
Thank you very much. Good morning to all. First of all, I want to thank Christian Nava for his invitation to present the results of the TLD system in these intercomparison exercises in the same way as I presented them at the last annual meeting in Belgrade. Beyond presenting these particular results of my laboratory, the idea is to provide a greater scope in the vision of the laboratories regarding in the Eurados intercomparisons organized from the Working Group 3 of Eurados. This is what I take the opportunity to encourage the participants of future intercomparisons to present their own results too. Well, going to the contents of my talk, First, I will introduce the participation of the TLD system in the intercomparisons organized from the Working Group 3. Then I will show you the TLD system of the TMAT. Next, I will tell you about how we do the dose and uncertainties calculations. And the results obtained in the intercomparisons are provided below to end with a couple of brief conclusions. Well, the two previous intercomparisons in 2014 and 2017, take into account 4 different PTV radiation fields of reference: free field, terrestrial component, cosmic radiation, and cesium irradiations. All of them are PTV reference radiation fields. The differences between both intercomparisons were basically 2. One is that the dose given with the cesium irradiation was different, and also was added an 90 angular irradiation in 2017. The figure shows you the results obtained by the TLD system in both intercomparisons. Look at the response of cesium that the TLD system obtained. In this case, take a look of this result, because after I will compare with the results of the last intercomparison that is the subject of this talk. Several scenarios were proposed in the last intercomparison, among which our laboratory chose outdoor exposure for 3 months. In any case, the proposal was to do 2 irradiations with doses of less than 0.5 millisievert in the middle of the exposure period. 6 dosimeters were used for outdoor exposure in free field, and 2 groups of 3 dosimeters, each for 300 and 150 microsieverts. The reported doses should be provided without transport dose corrections. As you know, it was made by the organizers. Going to the TLD system details, I want to present the equipment that we use regularly in the external dosimetry service in Tiamat. In the left corner, in the up left corner, we have the detector handling. We have small detectors that we manage in this black disc for the Harshov 5500 reader. Also, we have several treatments, heating treatments that we do in a PTW oven. And also we have for quality control and also for traceability, the strontium yttrium irradiator. That is a beta source. And well, about the dosimeter, we have a bag inside provided with a holder with 10 detectors. 6 are lithium fluoride magnesium titanium TLD100, and the other 4 are lithium fluoride 2, but with magnesium covered phosphor, that is a well-known hypersensitive detector. In this intercomparison, we participate with this system, GR200, but usually we use also TLD100 as a backup system if in the reading process of the GR200 doesn't work properly because some problems could happen. Pass the slide, please. Regarding main features, of the basic dosimetry system of the EMAT, it must be said that the system is validated according to based on the IEC 62387 standard. And also traceability and quality control procedures are applied to annual calibration in a metrology laboratory, as also by calculation, by individual calibration factor calculation of the detectors. We also participate in regular comparisons in the Spanish framework, and we are accredited according to the standard ISO 7025 since April 2012. This is in this slide at the right, you can see the model of the report that we sent in the last intercomparison too. Regarding the dose evaluation and measurement certainty, we have the 2 methods based on the GAM guide for the calculation of uncertainties. A general method that estimates expanded measurement certainty since from the application of the reader counts, reader calibration factor, energy and angular responses, the individual calibration factor calculation, and transport dose subtractions that are influence factors that partially provide the corresponding measurement certainty. And also a second method based on the standard deviation of the measurements. In this way, we calculate the dose mean value, the standard deviation, n-1, and apply the t distribution of the measurements. And in this sense, this value that here can be seen in the slide are the first, the general method is provided by the validation methods, and the second is this range of 4-13% have been calculated in these intercomparisons for the dosimeters that were used for background measurements. In this slide, I show you how we do the dose and uncertainty evaluation. The dose is calculated as a product of the corrected counts and the corresponding individual calibration factors. While the corrected counts are calculated by subtraction of the residual reading signals from a single glow curve analysis, the individual calibration factors are obtained by irradiation for a well-known dose using the beta irradiator before commented. After the dose is calculated for the 4 dosimeters, a mean value is obtained, and also, of course, the standard deviation, and then we calculate the mean value and the standard deviation are for the dosimeter, for each of the dosimeters that we use in the measurements. Here you are the results reported by the organizers according to all the procedure, and on the bottom part you can see the results of the background dosimeters. The values extracted from the mean value of these background dosimeters are here pointed as dosimeter results for low doses. And then the column of the response corresponds to the cesium response for 300 and 150 microsievert. Regarding the results of the individual results of each dosimeter that were irradiated at these doses, these low doses, the results are shown in the figure. As you can see, below 20% of the mean value of the 6 dosimeters can be established, and this value were used to subtract the transport dose to the irradiated dosimeters. The irradiated dosimeters, the results of the irradiated dosimeters is here presented, and here you can see that all the values are close to the reference, 150 and 300 microsieverts, and these results are close to the general method of uncertainty evaluation. When you consider the uncertainty of the metrology laboratory, you can establish the response to these values of dose of cesium reported dose. In the 3 dosimeters, you can see that the response is over the reference 1.0, and the uncertainties are so quite high that the before we have said about the background dosimeters that they don't consider the uncertainty provided by the background dose. And finally, I have drawn here a comparison of the cesium response for the three comparisons that were organized by the working group 3 of Eurados. And the results, as you can see, are absolutely similar. There is a small over-response in all the comparisons, and you can take a look about the calibration factor stability that is also drawn in the left part of the slide. The red points are the calibration factor when the intercomparison were done. So you can see that these 3 points, these 3 red points are very close, and for years also the stability has been guaranteed in the same way. So finished with my talk, I want to show you a few conclusions about the response of the TLD system, that is over the reference about a 5–8% in the 3 Eurados intercomparisons. We have a linear response, so in the range of 0.15–30 millisieverts. And also, well, we have proof that measurement uncertainty are consistent by the 2 methods used. So thank you very much, and I'll be happy to answer your questions or so wherever you want.
Thanks a lot, Rafael. So next in line, last but not least, we have Christian Laninski from the Cyberstorf laboratories. He was the coordinator of this intercomparison, let's say the head of the organization group, and he collected some feedback from the participants and shows you some conclusions from the side of the coordination of this intercomparison.
Okay, thank you, Christian. I'm happy to present here the feedback of some participants and our conclusions in our organization group about this intercomparison we organized the last year. And I hope we have some discussion about these issues. So let's start with the first conclusions. As we already heard from Julia, we had one participant who couldn't provide those meters to KIT in time. So that's a pity. But we had some flexibility in the deadlines, but not too much. And the same is, as we heard, one participant couldn't report his dose results due to customs problems. So that's also a pity, but okay, could not be avoided. And there are also 7 systems who were provided to KIT, to Karlsruhe, without the possibility of hanging them. So maybe we didn't stress this enough in our documents and announcements. So KIT colleagues had to find a solution, and they provided plastic bags for hanging these dosimeters, as you can see here in the photo, as an example. And what we saw at the end, we had some water inside these bags, which is of course not good for the dosimetry and was a sort of drawback for some systems. I also want to show you the results in a slightly different manner. So it's preliminary here because it's not the same way we showed it in our Uranus report. What I did, I made an average of the response values for each system, an average over the 3 irradiated dosimeters with 150 microsievert, and then a second average value for the response values of the 300 microsievert irradiations. So for each systems, we see here 2 data points instead of 6. So this should give maybe a better visibility, a better overview. And again, on the x-axis are the various dosimetry systems sorted according to their ranking numbers. So on the left side, the systems showed very small deviation to the ideal response value of 1, and to the right, there were slightly bigger deviations. And also these dashed lines you can see is just for guidance of the eye. Additionally, you see an arrow at the bottom showing the average ranking number, which is for all the systems 33, so the mean value. But on the next slides, I will show you the results of the 3 different groups. So here is the result for those meters taking part for 3 months in the outdoor position. These were 28 systems. And what we can see is that also these results are quite evenly distributed over the whole ranking numbers. So no real systematic difference to the overall, to all the other groups. And also the average ranking number is quite close, maybe slightly smaller, about 30. A similar picture can be seen in the next slide. These are the results for the 3 months indoor systems. So 23 systems were positioned there, as we saw in the pictures from Julia in an office. And again, the same result. All the participating systems were quite, let's say, evenly distributed over the whole range of ranking numbers, with an average ranking number, yes, close to 33. And finally, the third possibility was to take part 6 months in the outdoor region, and these were slightly less participants, so 14 systems took part there. And again, the same, I would say, quite the same results, evenly distributed over all the ranking numbers. And also the average is quite the same as for all the systems. So one could make some conclusions here that, in my opinion, most participated dosimetry systems performed really quite well. So the ISO limits we took as a criteria, I will go to this in the next slides, were quite fulfilled by most of the individual dosimeter results. What we saw in the last slides, we got quite similar overall results for the 3 measurement conditions, and also quite similar average response values for the 2 chosen reference dose levels, 150 microsieverts, so the slightly lower dose value, and 300 microsieverts. It has to be stressed that we chose an, let's say, reference radiation quality for most of the systems, so cesium gamma radiation. But the focus was not on determining influences of energy or angular dependencies or so, but the focus really on the capability of measuring a quite low dose. In my opinion, this is the most important capability of an area dosimetry systems, to really measure such low doses, because these are the typical doses or even lower encountered in real routine measurements in the field. The challenge was to measure these dose values despite background values in the range of about 200 microsieverts up to 1.6 millisieverts. So as you can see, these values are bigger than the additional irradiated dose values. So this is quite a challenge for the systems, and I will also show some conclusions at the end of this talk. I want to mention that the KIT calibration laboratory performed really very well. So the response values were for the most systems quite close to 1. There was only one irradiation which has to be repeated, but luckily this was for a system which had quite small variations in their background values. So they had only 3 dosimeters for the background value, for the average background value, but this was not a problem, luckily, for this participant. And the photo documentation, of course, of all the irradiation was perfect for me as a coordinator, because we could validate in case of questions, we validated the irradiations. We already heard about our criteria we chose. So we have an ISO standard 14146 shown here, provides criteria and performance limits for periodic evaluation of the dosimetry services, or actually systems. And we, in our organization group, we decided to choose the limits given here in this chapter 7.1.1. And this formula 2 here is this typical Trumpet curve we already saw. So for very low dose values, these limits are slightly increased compared to higher dose values. And this increasing values allows an over response and an under response of roughly a factor of 2. The conclusions I want to draw here is that we had quite a discussion in our group about the applicability of this ISO standard, and because area dosimeters were included in the last revision of these standards, 2018, and we really triggered by our intercomparison, we triggered now a current revision of this standard, and we participated in the first discussions. So this will take part now in the ISO TC groups, and hopefully we get finally really appropriate response limits for our dosimeters and useful requirements. For example, for the reference conditions, there are extra requirements which could be applied for area and personal dosimeters, in fact. An important point here, what is written here, is that we need actually information about the type of application of the dosimetry systems. In this intercomparison, we didn't ask about this application because we want to apply one limit, one Trumpet curve to all of them, but actually that's not really at the end let's say maybe a good choice, because we have really 2 different types of application. We have there the environmental monitoring, which is mostly outside in the outdoor areas. And we have on the other side the workplace monitoring, which is mostly inside, but with very different goals in this type of applications. So in the environment, we have to survey the doses for the general public, whereas at workplace monitoring applications, we have normally also exposed workers to be monitored with higher limits in the various regulations. And there could be, of course, systems providing both applications. So in the future, we will ask for this information and may apply really different criteria. But as we saw in our results, there are not really so different results for indoor and outdoor applications. Now I want to show a slide from the online platform. This is the registration, or the first page you can see if you go to this address, to this intercomparison dedicated home page, and you can see our intercomparison is here in the middle of the intercomparisons of personal dosimeters. So in the meantime, there are already 2 intercomparisons running. And the people, the participants had the possibility to use this platform to give all the information we asked for example, for the dosimetry systems as shown here. So this is an example of a participant who put their identification, for example, which is then a text included in the certificate. The measurement quantity was not a choice, so this was given here, H*10. Detector type, we already heard the number of detectors, reference radiation quality, then the choice between the 3 conditions we already heard. And finally, the participant stated a lower measurement limit here, and this was important to be sure not to provide too low dose values for certain systems. At the end, we finally provided an online survey for the participants. So after the whole intercomparison was finished, the certificates were distributed, we had some feedback, and then we said, okay, we really want to know better about the feedback from the participants. So they had the possibility to answer some questions here, and I want to show you the questions and some answers. So the first question was, has the intercomparison organization fulfilled your expectations? And the second question was, have your own intercomparison results fulfilled your own expectations? And here we provided 3 possibilities for rating. So positively yes, or negatively no, or somewhere in between. And we had finally 18 participants who answered this online survey. And one can conclude that most participants were really happy with the intercomparison, and mostly also with their own results, but maybe with some room for improvement. On this slide, there are all the other questions. In total, we had 10 questions, so a final question about general commands. But these here are the questions about all the aspects of our intercomparison, starting with the price, then with a question about the usage, the usability of the online platform, then the documents, the instructions in terms of conditions was a question, about the general time schedule, the measurement periods, and so on. We asked about the challenge of the low dose values and of the 3 measurement conditions, and finally of the documentation of the certificates and the report. And there are, as you can see, not so much answers at the end, but in this case, we didn't ask for a rating, so just to give yes or no or so, but we really only asked for text feedback, so we really can draw some conclusions, some discussions in our group. So what you can see in general, I would say the ranking is done by me, but in general, I grouped most of the answers were quite positively, so green colored here, especially as you can see for the usage of the online platform. So this was the first time we used this tool for our area dosimeter intercomparisons, and all the participants said they were quite happy about this. Yeah, I want to stress here a little bit more the critical answers here in yellow. So 2 participants gave intermediate answers, and 1 participant here in red gave some more critical aspects, and I want to show you in the next slide. At first, in green, there are I took some answers, just examples from all these answers to give you an impression about the feedback. So one participant said the doses are so low that it becomes difficult to determine precisely their value. And this is why the whole exercise is interesting. So this is quite a nice answer. And this was our goal to see if this is possible in such an international intercomparison. And it also was for the organization group quite a challenge, because we couldn't know if this is a whole problem for many systems, and luckily most systems performed well. Another answer was the graph with the ranking number is a good idea. I want to stress this here because, also in my opinion, it's much easier to compare results in these sorted graphs. And one can see a better overview of good systems on the left side, and of maybe not so good results on the right side for whatever reason. Yes, okay. In yellow here, an answer, we had irradiation during the transit, so the dose range were quite low for us. Yeah, that's true. Transit dose contribution is an issue, and I want to show this in my final slides and discuss this a little bit. And one answer in red here shown is about the same issue. It's not clear if a distinction is made between transport dose and natural background dose subtraction. This is a point we already discussed in our technical meeting we had in the meantime, and we will try to take this into account. It would be, of course, very interesting to get information about the actual transport doses. So in our intercomparison, these transport doses are included in the overall background dose. But of course, it would be interesting to see this contribution, and especially to get results for the natural background dose during the exposition of these 3 or 6 months. So we really, for this to make this possible, we have to provide, like PTB had the possibility in the previous intercomparisons, to provide a very shielded, low natural background place. Maybe not in an underground laboratory, but because this is such a huge amount of work and costs, of course, but maybe in a very heavily shielded room or so. But this is a real important feedback, and we will try to take this into account in the next intercomparisons. I want to show one slide from our questionnaire. We already heard from Arturo, we made these questionnaires and also provided a Uranus report about the results. And this is a figure 16 from this report about the dose calculation methods. And here you can see from the participants who answered these questionnaires, half of the participants really determine a net dose for their customers. So this is not in general the case, but about half of the participants do this. So they have to find a solution to subtract the transport dose in this case, the background dose here, and to have a good estimation of the background dose, which is not an easy task in the field, because you have to provide maybe a position where you have no extra artificial irradiations and so on. And the second bars here was a question: do you apply a transport correction? And many participants say yes. So they really try to estimate a transport dose for their customers, and then subtract the transport dose, which is not an easy task. So we should focus this also in our next intercomparisons. This is actually my last slide, or one of my last slides. It's concerning of the background dose. In our intercomparison, we calculated the background dose for each system as the average of 6 non-irradiated dosimeters. So it's quite a number of dosimeters, quite statistically, I would say, not bad average value. And here in this slide, you can see on the x-axis the calculated background dose values for the systems. So each plus sign here is a system. And most systems are here gathered to the left between about 200 and 400 microsieverts. And this is also the expected background dose values, taking a natural background dose of about 2 microsieverts per day. Then we end up for the 3 and 6 months in this region. So most systems were luckily in this region, so without an increased transport dose contribution. But some systems from 3 countries had really high background doses, which is a sort of drawback for them, of course, because also the uncertainty, the statistical uncertainty will increase due to this maybe additional irradiations during the transport, for example, by cargo scanning. So we have here countries like Japan, Italy, and UK who had increased values. But let's take Japan. It cannot easily be explained because they also took part in previous intercomparisons with much lower transport doses. Also from the UK, okay, we can maybe from the Brexit conclude that there are more cargo screenings now, but we had one participant from UK with not increased background dose values. And also the 4 systems from Italy, we already heard in the past that they changed their regulations for the transporting, so at the airports. But not all systems from Italy had these high values, so quite interestingly. And additionally, interestingly, the y-axis shown here is the background uncertainty, so the statistical uncertainty of these 6 values. And we see quite a spread of these statistical variations. We see that these variations are maybe below 10 microsievert, k equal to, so 95% confidence here. And some systems with higher variations up to this red dotted line. I want to also stress here the color of the plus symbols of the dosimeters is the green symbols showed no fails in the response values of the irradiated dosimeters. The orange one had 1 fail and the red one had more fails. And you can see actually the red plus signs symbols are for dosimeters with higher background doses. So it seems that there is a relation to the high background dose value, but not fully, because there are 2 plus symbols here with lower transport dose values, let's say around 500, 600 microsieverts, and with quite low variations, and there were other reasons for their failures. These participants had in average quite low response values, so one with about 0.3 instead of 1, and one about 0.5 instead of the ideal value 1. So this is the reason why they failed these criteria. And there is maybe some explanation or room for improvements. This could be the calibration. This could be some fading influences. This could be some other errors. So this has to be discussed within these groups. And maybe we get some feedback also from these, let's say, quite not so good results here. I mentioned this dashed line here at about 60 to 70 microsieverts. This is a value which can be calculated, at least approximately in the first estimate, a limit of the uncertainty variation of the background dose to have a detection limit of 150 microsieverts. So one can conclude that dosimeters below these limits should be capable of measuring correctly such low doses. Yeah, we will see in the future how we proceed with these low dose values. So finally, I want to say thank you to all the participants. So we are quite grateful that so many of you took part and were interested. And of course, thank you to the organization group, to Christian and all the colleagues. Thanks.
Okay, thank you for this presentation, Christian, and also thank you to all of the rest of the speakers. So we are at the end of our presentations now. Christian's presentation was the last, so we have still 20 more minutes time to deal with your questions. We have several questions in the chat, most of them by Rick Tanner, and I just read the questions. All of you speakers can maybe join and turn on their cameras and their microphones again. One wants to answer the question should do so. So Rick's first question was, did you consider using the performance limits given in IEC 62387? Christian, you already told us something about the trumpet curve and the limits we took from out of the 14146, and also told the persons here why we did so.
Yes, the trumpet curve of the ISO standard actually include these limits. So for the high dose values, which are typical for type testing with this IEC standard you mentioned, are a little bit tighter. And for the low dose values, the trumpet curve allows an increase of these limits. So we apply this ISO standard because it's actually really dedicated to the limit. And for the low dose values, it's good to have an increase because the uncertainty is increased compared to higher dose responses. I hope this gives some answer to your question.
Okay, thank you. Rick, maybe you can just mark your question in the chat with a thumbs up if your question is answered. Okay, then another question by Rick. For customers where the transit dose is not affected by the dose meters being X-rayed and the exposure is long, the transit dose is negligible? Question mark.
Yes, you really can see. Sorry that I answer.
No problem.
Yeah, you really can see that most of the systems were within the natural calculated background dose values for the 3 months, about 200 microsieverts, and higher, of course, for the 6 month. So we also had active dosimeters. They are positioned as a control. So Julian, you can tell about the active dosimeters, but this is not a real reference value. Because this would have more effort, like PTB provides, but it's a sort of control, and the natural background dose values were in this range. So if you have a background value with these values about 200 to 400 microsievert, you have really no increased transport dose.
Okay. So we have several statements or observations concerning this transport doses. I think everybody can just read them, but I didn't find a concrete answer in these statements. But there was one answer, especially for Rafael, for Fiona. Is there any benefit in doing trend analysis and using an overall mean value for calibration factor for your harsher systems?
Repeat, please, the question.
Okay, you can also read it in the Q&A if you click on the Q&A, but I repeat it for CMAT. Is there any benefit in doing trend analysis and using an overall mean value for calibration factor for your harsher system?
Well, exactly interesting in doing that depends on the relationship between the person who is asking about this. So.
Okay, so thank you. That was about it concerning the open questions. I already tried to answer 2 questions in the Q&A section you might have seen under the answered section. One of them was, what was the requirement to participate in the intercomparison? The thing is, we didn't make any special requirements as long as the participants could provide the number of dose meters given by the group and was able to read them and give all the results in the right time. Everybody could have taken part in it. And the second one was, how do you determine the reference value for the environmental part of the irradiation, outdoors and indoors? The thing is, we didn't state a reference value. We had several active measurement systems placed inside the bureau, let's say the indoor part, and outside, just to check if we have any unwanted exposition during the exposition of the dosimeters. And then that dose was calculated by subtracting the average dose of the non-irradiated dosimeters. But of course, done by participant, not one average dose from all over the dosimeters, but per participant. That was about it. Okay. Are there any other questions? If so, be quick to write them in the Q&A section, please.
Maybe I can give another comment to the transport dose. We really asked the participants not to subtract the transport dose, although they maybe do this in their routine procedures, because they had no information. We provide no information about the dates when the systems arrived at KIT and so on. So we really wanted to exclude this in this intercomparison. But for a future intercomparison, I already mentioned this, it could be really interesting to focus also on this part. And maybe we don't need a good reference value at the reference side, outside and inside. We could take, if we have enough participants, we can take the average or the median value, which is statistically also a very good value. We can make comparisons. So I think it's a good feedback to do this in the future.
Okay, thank you. As I see, there are no new questions. Babs, Kerstin, what do you propose? I think we could end this webinar at this point. Once again, thank you for speaking, for having the presentations. Thanks to the audience for listening to us, for some interesting questions and some points to discuss concerning the transport doses. And I'd say see you next time.
Great. Thanks a lot.